Imagine our Milky Way galaxy not as a serene spiral of stars, but as a sprawling, ancient city. A city built layer upon layer over billions of years. Its modern neighborhoods stand on top of medieval walls, which themselves were built over even more ancient foundations. Each layer tells a story of construction, of conflict, and of transformation. Astronomers today are acting as cosmic archaeologists, digging through these layers to uncover the dramatic history of our galactic home. This is the story of galactic archaeology. But instead of sifting through dust for pottery shards, these scientists sift through the light of stars. Each star is a perfect time capsule, a fossil carrying the chemical fingerprint of the time and place it was born. By studying these stellar fossils, we are piecing together an epic saga of galactic cannibalism and cosmic construction that shaped the Milky Way. The most spectacular chapters of this history are written in the vast, ghostly trails of stars known as stellar streams. The cosmic breadcrumbs left behind by galaxies our Milky Way consumed long ago. So how exactly do we read these stellar fossils? The two most vital clues are a star's chemical composition and its age. When the universe began, there was only hydrogen and helium. Every other element, what astronomers call metals, was forged inside stars and scattered into space when they died. Think of the carbon in your body, the oxygen you breathe, the iron in your blood. All of it is stardust. Each new generation of stars is born from a cosmic cloud slightly more enriched with these heavy elements than the last. This means a star's chemistry is a direct link to its age. An ancient star, born in the galaxy's infancy, will be extremely metal-poor. A young star like our Sun, born billions of years later, is metal-rich, built from the recycled remnants of countless previous stars. The primary tool for this analysis is spectroscopy. When starlight passes through a spectrograph, it splits into a rainbow, but this rainbow is crossed by dark lines. Each line is the unique, unforgeable signature of a specific chemical element absorbing light. It's like a stellar barcode. By reading this barcode, astronomers can determine the precise abundance of dozens of different elements in a single star, creating a rich chemical fingerprint. But what about a star's age? This has always been trickier, but the field of astroseismology has changed the game. It's the science of starquakes. Yes, stars quake. Sound waves and turbulence reverberate through a star's plasma, causing its brightness to flicker in tiny, predictable patterns. The frequency of these flickers is directly related to a star's internal structure and mass. And since a star's mass dictates how fast it burns its fuel, these seismic measurements allow us to determine stellar ages with incredible precision, often to within 10%. It's a reliable cosmic clock. With these tools, we can start excavating the different districts of our galactic city, encircling the entire galaxy as the vast, sparse halo. This is the home of the oldest stars, many over 12 billion years old. They are extremely metal-poor and travel on chaotic, random orbits, like relics from the galaxy's wild and lawless beginning. Then there's the main feature, the galactic disk. But it's not one structure, it's two. We live in the thin disk, a flat, spinning plane rich with gas and dust, where new stars are still being born. Our Sun is here, young and metal-rich, moving in an orderly, circular orbit. But embedded within it is a thick disk. It's puffier, twice the height of the thin disk. Its stars are much older, over 10 billion years old, more metal-poor, and move on faster, more eccentric orbits. The fact that we have two distinct disks is a huge clue that our galaxy's history wasn't a smooth process. It had at least two major phases of formation. And at the very heart of it all is the galactic bulge, a dense sphere of mostly ancient stars that formed in a furious burst during the galaxy's first billion years. For decades, our best models of the universe have predicted that large galaxies like the Milky Way, grew by merging with and consuming smaller dwarf galaxies. For a long time, this was just a theory. Galactic archaeology has found the smoking gun. When a small dwarf galaxy gets too close to the Milky Way, our galaxy's immense gravity acts like a tidal wave, ripping the smaller galaxy apart. Stars are pulled from it, forming long, looping ribbons of stellar debris that trace the victim's orbit. These are the stellar streams, ghostly rivers of stars flowing through the galactic halo, the undeniable proof of our galaxy's violent, cannibalistic past. Uncovering these ghostly rivers has been made possible by a new generation of massive astronomical surveys. The most important of these is the Gaia Space Observatory, launched by the European Space Agency. Gaia is the ultimate mapmaker. Its sole mission is to measure the precise positions, distances, and motions of stars, nearly 2 billion of them. It has created the most detailed 3D map of our galaxy ever conceived. Gaia gives us the where and the how fast for each star. This is the kinematic data that allows astronomers to spot groups of stars moving together, even if they are scattered across the sky. Gaia has been a revolution, turning this field into a precise, quantitative science. But Gaia needs partners. It needs ground-based spectroscopic surveys to provide the what, the chemical composition, and the final dimension of velocity. Surveys like Apogee, which uses infrared light to peer through the galaxy's dust clouds into its hidden core, and Gala in the southern hemisphere, which has provided detailed chemical fingerprints for nearly 1 million stars. Together, Gaia and its partners provide what we call 6D data: 3D position, 3D velocity, plus detailed chemistry and age for millions of stars. This is the raw material for rewriting our galaxy's history. And perhaps the most spectacular story to emerge from this data is the discovery of a lost giant, a massive dwarf galaxy that our Milky Way devoured between 8 and 11 billion years ago. This long-dead galaxy is known as Gaia-Enceladus, or more whimsically, the Gaia sausage. The sausage name comes from the extremely elongated, sausage-like shape its debris forms when you plot the velocities of its stars. The evidence is overwhelming. Astronomers found a huge population of stars in our galaxy's inner halo that all share a distinct chemical signature and move on bizarre, highly radial orbits, plunging toward and away from the galactic center like they don't belong here. This wasn't a minor snack. The Gaia sausage galaxy had a stellar mass of over 10 billion suns. This was the last major merger in our galaxy's history, and it was transformative. The collision was so violent that it literally puffed up the young, thin disk that existed at the time, creating the thick disk we see today. The debris from this single, ancient collision now makes up a huge fraction of the Milky Way's inner halo. Its discovery is a stunning confirmation of how galaxies grow, fundamentally rewriting our understanding of how our own home was assembled. The Gaia sausage is the largest ghost in our galactic graveyard, but it is far from the only one. The Sagittarius stream is a famous example, the ongoing disruption of a dwarf galaxy whose starry entrails now wrap around the Milky Way multiple times. Another, the Helmi stream, was one of the first to be found, the remains of a galaxy eaten 6 to 9 billion years ago. Each stream is another piece of the puzzle. This field is in its golden age, but the best may be yet to come. The James Webb Space Telescope is already peering back in time to see what the building blocks of galaxies like ours looked like in the early universe. And the upcoming Nancy Grace Roman Space Telescope will be a powerful engine for galactic archaeology, mapping the stellar halos and tidal streams of our neighboring galaxies, showing us the full diversity of galactic life stories. The ultimate goal is to create a complete movie of the Milky Way's evolution. By excavating these stellar debris fields and reading the stories written in starlight, cosmic archaeologists are not just uncovering the turbulent history of our galactic home. They are revealing the fundamental processes that shape galaxies across the entire universe and in doing so, revealing the magnificent, violent, and beautiful story of how we all came to be.